Hello, my name is Gopinath. I work in MRLIT as a development lead. I am one of the office holders along with David Passusti, Jason Victor, and Vikas Patel, who are trying to put together an iOS community and a forum. All four of us went through the Stanford lecture by Professor Paul Hegarty, and you will be going through that too if you are participating in this course. And I think we went through fall 2011 lectures. We found that lecture pretty interesting and exciting, and we learned a lot of new stuff. And I hope you will also learn and excited about this course. The professor does an excellent job of walking you through the course, explaining the concepts of iOS and everything you need to know to learn to program and create applications in iOS or apps in iOS. As you all might know by now, the language behind iOS is Objective C, and Objective C is an object oriented version of C, and it's a Mac invented thing. It's pretty much used only in Mac and for iOS development or Mac app development. The lectures from Stanford and the professor does a pretty good job explaining the fundamentals of Objective C because you need to know that. So he has a couple of sessions dedicated explaining what Objective C is, the fundamentals, and as you move along the course, you will also see explains the advanced capabilities of or the language constructs of Objective C as you move along to the end of the course. But iOS also uses primitive C data types and C calls, which the course assumes that you should know in advance or you should know. The course does not explain what those primitive C data types are and the differences between the primitive C data types and why they are not objects. So those things the course assumes that, or the professor assumes that you will know. And as most of us, I think almost all of us at some point would have dealt with C. We might have learned it in our colleges, or we might have programmed in C sometime in the past, or some of us may be doing it even now. So what we thought was when you go through the course, uh, we you will encounter those C data types, and during the time you have to go back and understand it or refresh it. So we thought, why can't we put together a small lecture which talks about the C data types as a refresher for the ones who know it already, or for the newcomers, just explain the fundamentals of those data types so that when you go through the course, you will not have a hard time or feel lost what those things mean. Okay. So what I'm going to do next is walk through 15 or 16 slides explaining or giving you an idea of what these things are. This is definitely not a C course. It's more of C data types course or a lecture. And I'll make it interesting by showing you live examples by writing code so that you will, rather than you just looking through the slides, you will also have an idea of, okay, how it is used in a program. Okay, with that said, let's get started. Okay, data types in C. At the higher level, C has only two data types, numeric and character. And that's pretty much it. There is nothing like Boolean or lists or hash maps. They all don't exist in C. You can create them by using these fundamental data types and create an higher level data type, which are pretty much called as a derived data types, but they are not part of the core C. They are all derived based on the application needs and so on. And fundamentally, this is what C has, numeric and character. Within numeric, you can see there's an integer and a floating point. They are numbers. Bottom line, the difference between an integer and a floating point is because the way the floating point is represented in the memory or in even in a storage versus how the integer is represented are different, and hence this differentiation between the numeric data type. But when it comes to character, it is just char, which is a one character representation of the character data type. So you may immediately think, okay, how do I represent a string in C? It's an array of character. That's how it is. There is no such thing as string as an object because C is not an object-oriented programming. So there is nothing like that. It's an array of characters which forms a string. So even in integer, you see multiple variations, right? You see short, int, long, 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 and same thing, floating point, you'll see float, double, long, double. They are all to support various ranges of the numbers which you're going to use. Short has a specific range, integer has a specific range, long and long long has some specific ranges, and they are all different sizes to hold the variable or a data type, and the size dictates the range that the variable can hold or a data type can hold. Okay, now let's go through this numeric data type in a little bit more detail. Why there are so many integer data type values? Like I said, to support various sizes, right? And if you look at the bottom table, it talks about the sizes supported by these various data types. And one thing you need to understand is you don't assume the sizes. So this is what I got it from the Mac. These are all the sizes. I'll show it to you in a demo in a short minute. These are all the sizes which are I took it from the Mac. Granted that today there is an attempt to standardize all these sizes across all the platforms, they are operating system dependent. Even if I think if you go to some ASICs processors with a small mobility devices, like say if you take Android or any other devices, you may say the sizes may be different, but you shouldn't always assume the sizes. It depends on the operating system. It depends on the platform which you're running it. So you use some sort of macro, which I'll go through in a minute. It will be defined in your hash defined files. You can use them, or use this function called size of to figure out the size of each and every data type. So do not assume the sizes of these data types when wherever you're programming, whichever platform or whichever operating system you're programming. Always use the size of function. Okay, now let's look at how you can create a C program in Mac, and the size of data types which I talked about. I'll start showing you how to create it by creating a simple C project and just explaining what that size of is. Okay, so to create simple C project, you go to your Xcode, say new project, and under this you will see iOS and OS X, and if you go to OS X and if you choose the application, you will see command line tool. Just let's choose this command line tool and hit next. It'll ask for a product name, so let's say simple C, and organization name is Merck, company identifier is Merck.com, and if you pull this down you will see C, C++, core data, and so on. Just choose C and then hit next. You'll be asked where you wanted to create this. So I'm going to say in my development, in my simple C folder is where I wanted to create this project. So now I'm creating this project. So what happened here is it created a stub, hello world stub, and put some code in there to print that hello world. And now you have created a successful C project using Xcode. Now let's look at what size of data types means here, right? So let me say short I. I'm defining a variable as a short. I is my variable. Short j, sorry, int j, and long k, and long l. Okay, now let me print those sizes of those variables. So in C, printf is like your std out in or C out in C++, or if you are used to Java, it's like a system.out. So here you need to specify the format string because it's not an object, of course, right? So you need to tell printf, hey, these are all my data types. Here I'm printing the number, which is pretty much the size. So everything is a size. So I'm just going to declare them as %d, which means they are all going to print a number, which is of type integer. And I'm going to say what's the size of my I, size of my j, size of my k, and size of l. So let's run this. So you get it, 2, 4, 8, 8. Size of an short is 2, short of an integer is 4, and size of an long and long are 8. So here long and long makes no difference. They're the same. Okay. Okay. Now we saw the sizes of all these data types. Now let's look at what those sizes mean. The size really dictates the range of the number which that data type can store, that integer data type can store. For instance, short has 2 bytes, which means that it can store up to 2 to the power of 15 minus 1. So obviously you'll be going, why not 2 to the power of 16 minus 1? I'll come to that in a minute. This is the formula. If you look at the table here, the right hand side, the rightmost column tells you the formula of the maximum value which the data type can store, which is 2 to the power of 15 minus 1. So obviously you would have noticed that 1 bit is missing from the 2 bytes for which the short has been allocated for, right? So same thing goes for integer long and long. So why there is a 1 bit less in the formula, or why that 1 bit is not used to store some additional capacity? The reason is that bit is the one which dictates the sign of your data, number. The 16th bit being 0 means that it's a positive number, and the 16th bit being 1 means it's a negative number. Okay. So with that, you can see that then short can hold a maximum of 32,767. That's the maximum value a short can hold, which is 7 FFF if you go by hexadecimal representation. So 2 bytes, which are represented as 4 nibbles, the leftmost nibble, which is 7. It's not F. If you fill it to the maximum capacity, then everything should be FFFF, right? But that's not the case because it's a positive number you're talking about here. So the first bit has to be 1. So the next 3 bits in that nibble is 111, which is 7. And the rest are all FFF. So that's the way it works. The first, or the 16th bit, or the leftmost bit, dictates the sign of your number. Okay, so let's quickly look at what that means. Okay, now there is something called unsigned in C. It's a qualifier to a data type. When you say unsigned, what you are declaring the data type to be is, this is going to be a positive value. That's it. I'm not going to look at the sign of this variable at all. I'm going to treat this as a positive number, or it's just a number, right, with an absolute value. And I wanted to tell the compiler that, okay, when you are using this, allocate the full capacity. Don't worry about that bit, 16th bit, which is being used in case of a short for indicating the sign. Don't worry about it. Use the full capacity. So you can really if you know that you are dealing only with absolute number, you don't really need to worry about that sign of it. And hence, if you by saying unsigned, you are extending that one bit and extending the capacity of that particular data type. And now it can store more. In the sense, it can now use 2 to the power of 8 for data type of short as opposed to 2 to the power of 50. Okay, so this is the advantage of but again, here you need to know that you are going to deal with absolute value, not with the sign values. So that way, it will give you the flexibility of defining your data type unsigned by extending this unused or the bit which is used for indicating the sign and opening it up to extend your capacity as well. Okay, let's see a quick demo for that as well. Okay, we are back to our Xcode. So let's remove whatever we typed in from the previous demo, and let's go ahead and start looking at this values, right? So I'm going to say short. Let's call this variable as I, and let me assign this value 7767. This is the maximum value. Now I am printing that value, and I'm going to see that value getting printed on my console. So I'm running it. It said build succeeded. Okay, it printed the value. Okay, now let me also print the how it is stored hexadecimal, how it's stored in nibbles, right? So for that you use %x, and it will take that value and try to print it in hexadecimal format. So you'll see 7FFF. So that's the way it works. Now let me make my I value by increasing its number to 768 and see what happens. Right now I have exceeded the capacity and I'm trying to take a bigger number and trying to shove it in I. So let's see what happens now. You see that even though it is 32768, but it is showing as negative 32768, which is incorrect. So now let's see what happens if I make it as a 9. Then it shows us as something 32767 with a negative value, and it shows something weird as FFFF80001. By the way, now here it shows 4 bytes, not 2 bytes anymore, right? It shows basically 8 nibbles, which is 4 bytes, but it's all completely messed up. Once you overflow the capacity, what you get is unpredictable results or unpredictable numbers. So this is the significance of the data type itself, the size, the range it can hold. Okay. Okay. Now let's have a quick look at how the data is stored. So we saw that, right? We printed the hexadecimal value of a number, and we saw what the nibbles are. So if you take that and try to represent this is how the number is stored. So here what I'm trying to show you here is a 2-byte number, which is a short, and the first byte obviously goes for a sign, and what the rest of the nibbles here say and give you the value of the number which is actually it's representing. So if you look at 5678, the hexadecimal value is 162E, and obviously the first nibble is 1, second nibble is 6, third nibble is 2, and the fourth nibble is E. So it also depends. It depends on whether it's a big endian or a little endian. But what I'm showing here is a pretty much a straight representation of how an hexadecimal is stored. But this doesn't necessarily translate into how it is stored in your system. And that is purely dictated by whether it's a little endian or a big endian, right? So let's look at quick demo and see how these values are and how you can print the hexadecimal values are and what that means for a negative number and a positive number. As usual, let's get rid of this. Let me call it as I equal to 3268 printf percentage %d percentage %x I and when I run them, you'll see 3268 and CC4. Okay, in my slide I think I am using a different one. Sorry, 5678. That's why. So it doesn't matter. But the bottom line is that's the value for the number which we used. Okay, now you can see 5678 and 162e. So that's the way that's represented. So if I use it as a negative value, then what happens? You'll see 5678 and E92. By the way, if you can notice if you look at the negative values and you try to print the hexadecimal equivalent of it, even though we know that short is a 2 byte, you will be, instead of seeing 4 nibbles, you will be seeing 8 nibbles. But forget this one, the FFFF part, but this is what it means. That's the way the printf formatting works on this hexadecimal values, but don't worry about this FFFF. It doesn't mean that it is this particular short is negative value, just means that printf handles the negative values and the hexadecimal values a little differently in formatting and printing it out. But the bottom line is this is what it is. E92 is what you need to be concerned about. Okay, now this particular slide now tells you the range of all these data types. So the range of assigned and unsigned. So obviously here you can look at it, how the range operates, right? So the minimum value is minus 2 to the power of 15 with a negative sign, and maximum value is 2 to the power of 15 minus 1, and that's the way it goes. So you can see this, use this as your reference for range. And as I said, again, it depends on the operating system. It all goes by the size, right? If the size is different, then the ranges are going to change as well. But this is a way of you knowing, okay, I'm declaring a variable in C. This is what my range is going to be, or that's what the range that variable is going to support. Okay. Now the next one is numeric data types. Okay, just before we get started into numeric data types, I just wanted to talk about a few things here. Numeric data type is very complex. Floating point data type. Floating point data type is very complex, the way it is stored. So I'm going to just give an overview of how it is stored, but I'm not going to go into details, and you don't need to know too. It's just, since we are talking about fundamentals, I'm just going to brush through those things. But really, the way the floating point data types are stored, they're pretty complex. Here, let's start with the sizes: float, double, and long double. Here you can see, obviously, long double is 16 bytes, pretty much all the capacity you need to store a number, right? Irrespective of that, most likely we'll be using float and double. Long double, I don't know whether we have a very complex application which deals with big numbers. I don't think you need a long double, but float and double are most often used, right? Okay, and the structure of float. How is the floating point structured and how it is stored in memory? It's not like integers, because if you look at floating point, it needs to deal with the sign bit first, of course. It has to say whether it's a positive or a negative. So here also unsigned applies, right? And the second is the precision of the floating or the decimal point it supports, and the exponent or exponential format which defines the whole number on what is your precision to be. So if you look at the structure of floating point numbers are represented in this format as m into b to the power of e, where m is the mantissa or the fractional part, b is the base, and e is the exponent. And the all the modern computer-based systems, it's always true. The base is always 2. And the most floating point representation, the mantissa, will be scaled between 1 and b. Okay, so what does this all mean, right? So if you look at a float here, which is 4 bytes, so I try to represent 4 bytes in here. So if you look at the leftmost bit, which is used for sign, then the next 7 bit is used for your exponent. If you look at it, m into b to the power of e, and that's the exponent piece of it. What does that exponent piece means? It is represented in an XS127 notation. So XS127 notation is 127 is 0. Anything up, it linearly goes upwards or downwards from 127. So this 7-bit can represent 127. So 127 means it's 0. 128 means 1. 129 means 2, and so on. So what if, let's say, if the 7-bit represents 130, which is 3, so it means that it's 2 to the power of 3. That's what it is. Remember, our base is always 2, right? And the next bits, or the next 3 bytes, are used for representing your mantissa, or the fractional part. So the first being 1 by 2, the second bit being 1 by 4, and the third bit being 1 by 8, and so on. So you can see it scales into a very high precision by using 3 bytes for representing your precision. Okay, so this is not straightforward like integer, where it is stored in an hexadecimal. You take it and the binary value gives you the actual value, but this is not the case at all. The case how the floating point is stored is very complex. So let's look at an example so that we can understand this better, right? So let's look at how 1.5 is stored. So the first example here, if you see my cursor, the first one says 0. That means obviously it's a positive number. Here the second one is 127, which basically tells me that it's 2 to the power of 0. Basically the exponent part is 0. So base is 2, so 2 to the power of 0, which is 1. And the mantissa is the first bit, which is 1 by 2, second bit is 1 by 4, and so on. So if you really look at it, the mantissa is 0.5. So the value is 1.5 into 2 to the power of 0, which is 1.5. So that's how 1.5 is represented in a floating point notation. Similarly, the next one, you look at it, the first bit is 0. So obviously it means that it's a positive number. And the exponent is 125, which is by XS127 notation, it is minus 2, because it's 2 lesser than 127. So the exponent is minus 2 and the base is 2, so it's 2 to the power of minus 2, which is 0.25. Then the mantissa is 0.5. So the value is, because only the first bit is set, so it's 1 by 2, it's 0.5. So the value is 1.5 into 0.25, which is 0.375. So you take this one, which is 0.5, and add it to 1, which is always our non-fractional part, just 1, and that gives you 1.5. Not add, you basically append it. And then you look at the XS127 notation, which talks about, which gives you minus 2, which is 125, or 127 minus 125, 125 minus 127, which is minus 2. So the base is 2, 2 to the power of minus 2 is 0.25, and then if you apply this m into b to the power of e, you will get 0.375. Similarly, the next example talks about integer 8, which is minus 8 in this case. The first bit is 1, which is negative. So followed by XS127 notation, which is 3 here, because the value is 130. So 130 minus 127, 3. 2 to the power of 3, 8. The fractional part is nothing. Everything is 0. So 1 into 2 to the power of 3, and it's a negative value, so it's minus 8. Okay, I hope I didn't confuse, but again, this is something which you really wanted to understand and write some row level C code. You need to understand this to this extent, but just I'm showing this to basically highlight integers and floating points are different and they're stored different as well. Okay. Character data types, right? So character data types are simply only one, which is char, and everything else is derived out of it. So what that means is, if I am defining a string, or if I want a string, I need to basically define it as an array. So here, if you see it, a character data type of alphabets of 27. So I am just storing, let's say, A to Z into a string. I have to define an array of character, which is size or capacity of 27. By the way, you notice it in C, everything starts with 0. That's like Java, right? Index is always 0. Actually, Java is like C, but bottom line is, if you know Java, it's similar. So it starts with 0. And if you look at it, when you say alphabets of 27, you are allocating 27 space. Technically, you need to allocate only 26 spaces, right? 0 to 25, right? But here we are saying 27 because in C, since everything is raw, you need to define an end point of a character. So the end point is always represented by a string 0x00 or null string. So if you don't define this, that means you will get inconsistent results. So any string operations on C assumes a string is terminated by this character 0x00. You may even define 100 characters, but it's variable. It's not that all the 100 will be printed all the time, or all the 100 characters will be used in all your string operations all the time. The capacity of the string, or the limit of the string, is defined by the null termination character. This is also called as null termination, which is the 0x00, which is basically a 0 string or null value or 0 ASCII value, right? So let's take a look at that for a minute, right? So let's define a character, alphabets of 27, right? Then I'll say alphabets. I am just saying A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, X, Y, Z. Okay, by the way, just think, here you cannot equate it. So you assigned 27 spaces for alpha. You just cannot equate it like this. The way you use it something called as a string copy. So you basically say that copy this string to this alpha variable, or alpha, which is a data type of character, which has 27 in length, with this particular string. What string copy does is, it copies this and it puts your null termination also. Okay. Now if I print this, I should be able to see my entire string. Now let me do this here. I'm just going to go and say alpha of 7 equal to 0x00, and then print this again. So what should I be seeing now? G. So what's happening here is, any of the operations, further operations now, they stop at 0x00. So that's the way you say my string is complete, right? My string completes with this delimiter, or with this type of a null termination character. So that's what it is. So what that means is, my 7th position, or in a way 8th position, starts with 0, right? 8th position is overwritten with null. So that means, now if you really look at the string, I have A, B, C, D, E, F, G. H is overwritten with 0x00, but the rest also remains there. It's there in the memory, but you will not be able to use it in a normal string operations, because all your string operations thinks that, okay, the string ends at G. That's it, because my H, whatever is in the next position or the next part of the array, is basically telling you that it's null, so that means it's done, right? So that's what it is. I can go ahead and print the rest of this thing also. I can do a way like this and say starting from 8. If I print this, what will happen now? I'm saying go print from that 8th character. So now if you really look at it, I have two things, right? Alpha and start anything after 8th character. That will print up to Z, which is then after Z there is a null. So it's assumed that that's the end. So it's printing up to that. So if I run this, I will see A, B, C, D, F, G, H is null, and then it starts printing the rest. Instead of 8, if I put 7, what will happen? It will not print anything. That's correct. So it's basically it prints A, B, C, D, F, G, and from 7 it starts with null. So that means assuming it's a null string. So that's what's happening. Okay, so far. Okay, so pointers. Pointers is not a data type. It's more of a address pointing to a data type. So you declare pointer pretty much pointing to anything. It doesn't matter what data type it's pointing to. You point to an integer, you point to a short, you point to a character, or you point to a piece of memory fragment in a code. So pointer can pretty much point to anything, and that's not a data type. Okay. Pointer actually stores the address of where the data type is there or stored. For instance, a pointer points to a short data type. What that means is a pointer is pointing to a location where that start data type is stored. And the way you say define a pointer is with a star. So if you want to define an integer pointer, you say int star a, where a is the variable, right? You can also define a short by saying short star s. So that's the way you define a pointer. So in a nutshell, pointer points to a data type, and the data type is stored in some memory address, and pointer actually holds the value of the memory wherein which the particular variable or data type is stored. So let's just see this quickly, how it is stored. So you see this, it's stored in, let's take a pointer p, which is a short, which is pointing to a short. So that's the way you declare short star p, and it's pointing to a variable in the memory called short s, and you are pointing it to that particular address. So your short p, that itself is stored in some memory location, and you can see that the size of that is pretty much the size to hold the memory address, and the content of that particular variable is another memory address which points to where the short variable itself is stored and the value of the short variable itself. So I think it'll become clear if I just show you a quick demo, and that will make it easy to understand. So let's go back. So I just wrote this quickly before I started the topic on pointers. So I defined a variable called es, and I'm assigning it a value 5098, and I'm assigning a pointer which points to a short. Basically, I'm telling the compiler that the pointer p is pointing to a short. So in the runtime, you can point it to anything. It really doesn't matter. This is just a compiler to understand that this pointer is pointing to a short variable, so that if it has to check any syntax associated with the short, it will do that very effectively. And the way you do an address in C is by saying ampersand. Ampersand means the address. So when you say ampersand yes, that means you're referring its address of where the variable is stored. So P is pointing to ampersand S, which is P is now containing the value of the um, address on where the short variable S is stored. So let me run this quickly and you will see this. So by the way, for pointer's address, you don't have to use ampersand because the pointer itself is an address. So you just say P, and I wanted to I'm just printing the address in hexadecimal format, and I'm also printing the address of S. And I'm also trying to print the address of P, which is the actually where P is stored. And S is the value of the actual value and the hexadecimal value of the variable itself. Okay, so that's what I showed in the slide, where pointer P's address is this, and it contains the address of S, because if you recall, I'm assigning P equal to ampersand S, and then I'm taking the address of S and assigning it to P. So that's why the address of S is stored in P, and then short is that value which I assigned in here, which is 5098, and that translates into an hexadecimal equivalent of 13E. So this is what pointer is. Pointer is just pointing to a data type, and it can point to pretty much any data type, and the way you declare them is with a star. Okay. Okay, now we have seen how the pointer stores the information, right? So now P and S. P is pointing to where the S is, and S has a value of 5098. Now let me try to do something different here by assigning P a place from the heap, and only P as the pointer pointing to the memory in the heap, and there is no other variable referring to that particular memory in the heap. So the way to do this is there is a C function called malloc, where you allocate the memory and you say how much memory you want. Basically, I want size of short, and I allocate it, and memory malloc returns you the address which is stored in the P. Now this malloc is an address in the heap, which I take it and assign it to P. Now if I go, and then I can basically start assigning some values to that particular memory location by using this pointer, which is star P, and say 1, 2, 3, 4, 5. So this is the value I am assigning to that location in the heap through this pointer P. Note that in the previous case, P just points to an already statically allocated variable S during the compile time, and it points to that variable. Now this happens in runtime, where P gets a chunk of memory, which is the size of short, and assigns it to itself and says, okay, now from now on I'm going to point to this new place, and it dereferences the memory. Basically it doesn't dereference it, we are overwriting the value of address of S, which was stored in the P originally, with the newly allocated space from the heap. Okay, so now if I go back and say percentage X and say percentage, let's put the value also. Now P will still have the same value because the pointer is still the same and it's a statically allocated value. And now I'm also printing the value of the P, which is going to give you 1, 2, 3, 4, 5. Okay, so what's the difference here? Now I overwrote the content of P to this new memory address 100E0, and of course if you put one more variable here, let me put one more format and print the address of the P itself, which shouldn't change, which should basically be the address of the P whatever we printed in here, right? So it should be the same, that shouldn't change at all, and that should be this value which you're seeing it here. But now what P is pointing to has changed. So let's run this quickly. So you can see the P is the same, right? Because it's statically allocated a pointer address. Now it's pointing to 100E0, and 100E0 contains a value of 1, 2, 3, 4, 5. Now here is the important thing which I think every C programmer would have at some point come across is memory leak. What does that mean? Now let me go back and reassign it to yes. What just happened right now? We lost all the references to this dynamically or runtime allocated heap, which is memory from a heap which is of size short, by overwriting the value of p. In the previous case, we always asked the yes. So even if we overwrote p with this malloc, we still yes is pointing to the memory location, which is fine. But now what happened is just we allocated where there is just a runtime pointer which basically points to a address in a heap. Now you overwrote this again with the value of s, and this is exactly what a memory leak means. Now if you keep doing this in a loop, what will happen? You keep asking memory and you keep overwriting them with something else. Those and all will be held, and your program size or data size goes bigger and bigger. At some point it exceeds and it will crash. Typically what you do is you execute something called as a free, which basically frees that memory before you start assigning something. Oh, sorry, you don't do it here. You do it here, it's going to crash. You do it here. What is going to crash is if you free it and try to print it, because it's a freed memory and you're trying to print it, it'll crash. So you do it once you are done with that variable, and then you can start freeing them and start assigning with some other value. This is the way you avoid memory leak. So what just happened here is you allocated a memory and you freed it before you reassigning to something else. If in the sequence you basically took an already existing short and try to point your pointer to that short variable, then you try to do a runtime allocation from the heap and try to assign it to your pointer, and then what you did is further freed that before reassigning it to avoid memory leak. Okay, structures. Structures are a mechanism to define complex data types in C. It's probably, if you draw a parallel with the 4GL languages, they are pretty much record types. So you can treat them as record types. If you look at how the concepts of class, which we are using in Java and C, C#, whatever the object-oriented programming languages are, they evolve from structures, where structure just lets you combine or group real only variables. The classes take it to the next level of variables and their characteristics through methods or messages, whatever we want to call them, is what a class is, and that's the distinction. So structure is a grouping of variables. It can be any variables, any data types, or pointers, multiple arrays. It doesn't matter. Whatever, you can package them into a structure and you can use them in your programs. So just an example here, I have defined a complex number structure with a real part and an imaginary part. They both are floats. And also have coordinate systems where a float of x and float of y. Again, they are both basically represent the x and y values in a coordinate system, two-dimensional coordinate system. Okay. Then how to use them is you just define them by saying struct coordinate and put a variable. So the struct coordinate is more of the data type which you defined, which combines of other primitive data types packaged together, and then you define an instance of a variable co1 and co2, and then you start referring them with .x notation. co1.x is 1, co1.y is 3, and so on. So that's the way you define your structures. Okay, let's just go through quickly Xcode and see how it looks. So how do I define a structure? I say struct, let it call it as complex number, and I'll call it as int real part and int imaginary part. This is my structure. Now how do I use them? I just say struct complex number A. So A is a variable. Sorry, A is a variable of type complex number, which is defined through a struct. And the same thing here, B, which is also a complex number. Now I say A dot imaginary part equal to 1, A dot uh, real part equal to 1 as well. So this is the way I use them. And in Objective-C, you will encounter this. So if you are using core graphics and all, you'll see the CG point, CG size. They are all C structures, primitive structures. That's what you will be seeing. This primitive C structures be heavily used in Objective-C and in iOS SDKs. Okay. Then you can also put a pointer to a structure, same way, by saying star p. Oh, it's giving me an error. Oh, p is already defined, so let me call it as p1. I already defined a p which is pointing to a short. Now let me call it as p1 and point it to a complex number. And then here the difference is I cannot just use them yet because I have not assigned any memory or any previous allocated structure. So I have two options here. I can either allocate a previous assigned structure, again ampersand A, or I can address of A, which is already an statically instantiated a complex number, and I'm assigning to this pointer. Now my P1 is pointing to A. Or I can also, let me define another variable, struct complex number, say let me call this P2. Now let me assign allocate dynamically during runtime. So the way I do it, malloc size of struct complex number. Okay. Why this is giving me an error? Let me see. Oh, sorry, it's a pointer. Okay, so this is how I allocate my memory dynamically for a structure. But there's a key difference, right? When a pointer, you cannot access the elements or the variables within the structure by dot. You have to use this funky notation, which is dash followed by a greater than symbol, which is pretty much like an arrow, right? So that's the way you access them. And the same thing is real part. This is the way you access them. So the structure, the one thing you need to note about is the pointers. If it's a pointer, it's referred with dash and a greater than symbol. And if it's a static instantiation, you refer them with p dot. So dot notation. So that's the difference you need to understand. So that's pretty much it. So you will be seeing this a lot in your iOS SDKs. You will be using this primitive C style data type, which is a structure, and especially around core graphics, you will see this a lot. Okay, structures. Structures are a mechanism to define complex data types in C. It's probably, if you draw a parallel with the 4GL languages, they are pretty much record types. So you can treat them as record types. If you look at how the concepts of class, which we are using in Java and C, C Sharp, whatever the object-oriented programming languages are, they evolve from structures, where structure just lets you combine or group real only variables. The classes take it to the next level of variables and their characteristics through methods or messages, whatever we want to call them, is what a class is, and that's the distinction. So structure is a grouping of variables. It can be any variables, any data types, or pointers, multiple arrays. It doesn't matter. Whatever, you can package them into a structure and you can use them in your programs. So just an example here, I have defined a complex number structure with a real part and an imaginary part. They both are floats. and also have coordinate systems where a float of x and float of y. Again, they are both basically represent the x and y values in a coordinate system, two-dimensional coordinate system. Okay. Then how to use them is you just define them by saying struct coordinate and put a variable. So the struct coordinate is more of the data type which you defined, which combines of other primitive data types packaged together. And then you define an instance of a variable CO1 and CO2. And then you start referring them with .x notation. CO1.x is 1, CO1.y is 3, and so on. So that's the way you define your structures. Okay, let's just go through quickly Xcode and see how it looks. So how do I define a structure? I say struct, let it call it as complex number, and I'll call it as int real part and int imaginary part. This is my structure. Now how do I use them? I just say struct complex number a. So a is a variable. Sorry, a is a variable of type complex number, which is defined through a struct. And the same thing here, b, which is also a complex number. Now I say a dot imaginary part equal to 1, a dot real part equal to 1 as well. So this is the way I use them. And in Objective-C, you will encounter this. So if you are using core graphics and all, you'll see the CG point, CG size. They are all C structures, primitive structures. That's what you will be seeing. The primitive C structures be heavily used in Objective-C and in iOS SDKs. Okay. Then you can also put a pointer to a structure, same way, by saying star p. Oh, it's giving me an error. Oh, p is already defined, so let me call it as p1. I already defined a p which is pointing to a short. Now let me call it as p1 and point it to a complex number. And then here the difference is I cannot just use them yet because I have not assigned any memory or any previous allocated structure. So I have two options here. I can either allocate a previous assigned structure, again ampersand a, or I can address of a, which is already an statically instantiated complex number, and I'm assigning to this pointer. Now my p1 is pointing to a. Or I can also, let me define another variable, struct complex number, say let me call this p2. Now let me assign allocate dynamically during runtime. So the way I do it, malloc size of struct complex number. Okay. Why is this giving me an error? Let me see. Oh, sorry, it's a pointer. Okay, so this is how I allocate my memory dynamically for a structure. But there is a key difference, right? When a pointer, you cannot access the elements or the variables within the structure by dot. You have to use this funky notation, which is dash followed by a greater than symbol, which is pretty much like an arrow, right? So that's the way you access them. And the same thing is real part. This is the way you access them. So the structure, the one thing you need to note about is the pointers. If it's a pointer, it's referred with dash and a greater than symbol. And if it's a static instantiation, you refer them with p dot. So dot notation. So that's the difference you need to understand. So that's pretty much it. So you will be seeing this a lot in your iOS SDKs. You will be using this primitive C style data type, which is a structure, and especially around core graphics, you will see this a lot. Okay, enumerations. What are enumerations? They are named set of integer constants. So let's assume you have a need for defining weekdays, and you wanted to use those weekdays as an index for an array. So let's say I have a aggregated value of some metrics information for each and every day in a week, and I want to store them in an array. Sunday being at 0 and Saturday being at 6. Remember, C always starts with 0. So I have to say a of 0, or the aggregate value of 0 equal to something, and aggregate value of 3 equal to something, which actually what I'm meaning there is Wednesday. So I have to remember all these numbers through, and I have to put them in some sort of a documentation or some sort of a note to say that, hey, this is what it means. I'm storing my value of 0 in an array, and that value represents the aggregated value or the metrics associated with Sunday. So this is a way. It's not a neat way. It's not a easily readable way from the documentation perspective, from the code perspective. So what C offers is a mechanism called enumeration, where you define your integer constants and you enumerate them with values. So here is an example in weekdays, Sunday to Saturday, where Sunday starts with 0 and Saturday ends with 6. So Sunday equal to 0, then it goes one by one increment from that point onwards, where Monday will be 1, Tuesday will be 2, and so on. For some reason, if you do not want Tuesday to be 2 and you want it to be 4 and Wednesday to be 5, then you can also define that by going to Tuesday and saying equal to 4. From that point onwards, it gets reset into 4, 5, 6, 7, and 8. So that's the way it works. The another example is a Boolean, where 0 is false, true is 1. So I have an enumeration called Boolean, and 0 starts with, it starts with 0, so false is obviously 0 and true is 1. Okay? Okay, let's look at a quick demo. So I'm declaring my enumeration called weekdays. So you know what, let's keep it simple. I'm calling it as directions, and I'm calling it as north, south, east, west. Okay, now I'm declaring another sort of a variable which is of type directions, and I'm calling it as d1. So what I've just did here is I declared a variable called d1, and I said, okay, it is going to be either north, south, east, or west. That's what I said here. Okay, so now if you can see, and if you want to print this value and see, let's just do only a couple of variables. Okay, I want to print my value of east and my value of west, and let's run it and see what happens. It's 2 and 3, so 0, 1, 2 and 3, so 2 and 3, that's what it is. Now if you look at it, it gives a clean way of defining things rather than zeros and 0, 1, 2, or 3 as indexes. So now let's say I wanted to aggregate a population, or let's say population for a minute, right? So population of this North America, South America, East and West. We just want to divide this into 4 and take the population values. So now I have, let's say, a long variable called population array of, say, 4. Okay, now I go and say population of north equal to I'm just putting a number which does not make sense. I'm just saying 100, meaning let's say 100, sorry, 10, let's say that means 10 million. Okay, it's all multiples, it's a millions. Okay, so now let's say population of south is 6 million, and population of east is 5 million, and population of west is, let's say, 10 million again. So now it reads nice. I'm really using this in a nice way, rather than saying population of north is 0, 1, 2, and 3, and then people have to put through. I have to put some documentation here saying 0 means north, 2 means, 2 means east, and so on. So the enumeration basically gives you this nice way of representing things, and you take a set of constants and enumerate them so that you can use them in a meaningful way in your programs going forward or in your code going forward. Okay. Now here we are at the final part of this presentation is the type def. Type def is a way of defining your own data type. I mean, let's say you have structures, you defined a structure and you wanted to, every time you use it, you say struct this and start assigning variables or pointers to it. Rather, what if I give some meaningful name or a synonym to it and I refer using that because it reads nice, it reads pretty well in the code, and that also gives me a good documentation for my code, right? So type def is nothing but letting you define your own data types. So let's quickly take a look at what that means. So here we have defined complex numbers A, complex number B. These are two my structs. Now when I define variables to this, I am defining it like this way: struct complex number A, struct complex number B, and so on. What if I type def this? Struct complex number, and I call it as complex numbers. Okay, then I can go back and replace this with complex numbers. So now if you really look at it, it reads nice, and also it tells me, okay, I have a data type called complex numbers. This is my own custom defined or derived data type. Similarly, I can do this here as well. Pointer to my complex numbers. Okay, so I can start using that. It's just not limited to structures. You can pretty much type def anything. So I can type def this also to directions. Then I can go here and say directions d1. So now it gives me a neat way. So if you really look at it, this looks like a variable to you. This looks like a data type to you. And in a way, complex number becomes my data type. This is the data type I defined using two integers and using it for one for a real part and one for an imaginary part. And I also defined my enumerated called directions, and I use them for enumerating the directions north, south, east, and west. So it becomes more of a derived data type, and it's my data type. I define my own data type in this case. Okay. I can also go just take, instead of calling it as long population 4, I also want to call this as population count, right? And I wanted to type def this as population count and population count equal to an array of population 4. So I can pretty much define any data type, even if it's primitive. It doesn't matter. You can type def them and start calling it your own. So that's what type def is. So in your iOS courses, which you're going to go through, you will see them, all your graphics structures, which I said, like CG size, CG point, CG rect. They are all nothing but structures. They are type def to CG point, CG rect, and CG size, whatever those things which are referred in iOS as, and that's how they are used. So here I'm showing a CG point, which you'll be learning soon, which is nothing but a struct with x, y, and z, where x is a x-axis value, y-axis value, and z-axis value. By the way, in iOS, these core graphics, they are floats, but here I define my own, and I'm calling it as double. And I don't think iOS SDKs or the core graphics SDKs has the third dimension, which is z. It has only x and y, and they are floats. So this is a way of defining your own data types. Okay. One other thing which I didn't cover here, it's called union. I think nowadays I don't think anybody uses union anymore. This union is nothing but a structure, and what it does is, if you are defining three elements within a union in a structure, it allocates the value for the maximum variable size, and that is shared across these multiple variables. So in a way, if I define a union x and y, x being a short and y being a int, only size of int is allocated, and that is shared between these two variables x and y. In a way, x is typecasted as short and use the storage of integer. So it's really not that used nowadays. That's a way of sharing your memory, and because if you know that you're using a number and you wanted to use a union mechanism to share it effectively, it was a mechanism for that, and also it's an indirect typecasting mechanism. But I don't think that is really used that much nowadays. You can refer that. It's pretty much the same syntax as a struct. Instead of calling a struct, you call it as a union. And that brings us to the end of this lecture. And I hope you liked it, and you hope you understood few concepts of C and or it refreshed if you are used to be a C programmer. In case if you have any questions, please feel free to reach out to me. My name is Gopinath again, and I am located in Rahway. You can send me an email. My email address, I'll post it along with the slides, and you can contact me through email as well. Okay, thank you very much. See you.